Is that what people are saying on
You can see over
on Zoom and YouTube too? Okay. So start?
there. Let me start on this.
Yeah. So I guess the issue is not the language, issue is the accent. And I'll try to do some phrases in Urdu too. Good to see you, Dr. Bharat.
This is Dr. Naman, currently working on DICE project and also head of NAPTEC project as well.
Okay,
He's from mechanical department, sir.
mechanical engineering. And Dr. Bharat,
He's
how
actually
long are you here? At the university, I have you might be transitioning. 20 more days. Drain for Pakistan. Huh? Well, I mean, I can be saying that because I spent a lot of my life outside too. So.
We are starting the session.
Are you also students here? Yes. So in EE right now, people who are working on the real side side, how many students do we have? So those could be working on the side. I guess we can talk later.
Hello. Assalamu alaikum, respected participants.
Assalamu alaikum, respected participants. Today we are having session on IC development cycle from our esteemed speaker, Mr. Shabbir Halai. Mr. Shabbir, sir, I'm pronouncing your name.
Yeah.
Sorry for the mispronunciation, sir. It's Shabbir Halai. Mr. Shabbir Halai, or as called Dr. Shabbir Halai.
I know a doctor. Shabbir. You can just call me Shabbir.
Mr. Shabbir has an extensive industry experience in IC, integrated circuits, development from concept to commercialization. He is committed to democratize success of semiconductor technology of developing countries, including his native country of Pakistan. So now I am moving forward to start this session formally. Sir Shabbir, are you comfortable with the session?
Yeah.
Over to Sir Shabbir. Thank you, sir.
Thank you very much. Welcome everyone who is present here and people who are present online. It's my pleasure to. How come this is? Yeah, it's posted on the presentation. Presentation more.
All the participants, please use the washroom mic if you have any question. And also, please turn your mobile phones on silent mode. Thank you.
Sir, can I move? No.
Okay. Okay. Let's get started. Okay, thank you everyone for making the time. It is my pleasure to be here. And I guess I can have this discussion in a very informal way. So stop me if you have any questions, if I get too technical, because I don't know what is the audience level. So I'll try to go up if I go too technical. So the reason I'm here is twofold. Is, as you would have all heard, that there is a big demand now for the countries to go independent in their IC development cycle. It almost has become an issue of how can a country be sovereign or independent if they have to rely on the chips for other countries. So Pakistan is also coming up with its own national semiconductor plan that we want to do more IC design here and eventually go into flight manufacturing cycle. I can talk about the Pakistan National Semiconductor Plan later on, but let's first go into the purpose of the meeting here today. Just in case if people are interested, that's my quick bio. I have been in the IC development industry for the last 25 years, worked for companies from startups to established big companies like Rockwell Semiconductor, Connexent, and most recently with Qualcomm. Okay. I got an electrical and computer engineering degree from University of Texas at Austin, and my focus was mostly on IC fabrication. So I'm very familiar with the back end, doing like the wafer fab. I've also got an executive management degree from the University of San Diego, California, and then that wasn't enough. I went back and got a master's in psychology and counseling too, because I find that as I work with people, engineers, to have the human skills trained in that is very helpful. Okay, so the topic of the talk today. Okay. Okay, can you guys hear me? And are people online? How many people we have? We got Dr. Hamad Chima and Dr. Tessie. Welcome, guys. So I have made a flow chart from my industry experience about IC design cycles. And if you look on the diagram here, the first 8 blocks are more related to IC design, and the last 4 stages are more towards IC manufacturing. Depending on the interest level of the students or attendees, I can go into detail of any of the stage more or less. So one thing what I've done for the audience here is, as I've gone through the block diagram, I have highlighted what are the stages that can be done in Pakistan. So everywhere, every stage when you see a Pakistani flag, that means that Pakistan can easily go in there because the investment and the capital investment is not that high in those stages. Okay, so from what we have seen, so here is the block diagram, and the first step, let's talk about like the chip customer specification, and you notice that I removed the Pakistani flag from that block here, because right now Pakistan is not doing any IC design as I know. So if we go into it, we would have to rely on the specifications to come from the customers. Okay, but in a regular development cycle, if you're working on a microprocessor or a modem or microcontroller, the specification usually comes from the customer, and they interface with the marketing department, and they first generate a marketing specification or the chip customer specification. They bring it into the engineering team. Engineering team looks at the requirements, and there's usually constraints, whether it's engineering constraint, it's power, area, schedule, time, and they go back and forth. And so basically what happens that the marketing specification or the customer specification gets converted into an engineering specification. Then it has to be signed off, because if you had infinite time and infinite money, you could have done everything. So once that's been agreed upon, that becomes your main document, like the engineering specification. And usually what happens after that, the engineering team sits down and starts working on the architectural block diagram, because here is the RAM, here is the graphics code, here's the video code, depending on what, and they start with the block diagram first. And from that point on, a lot of time if the chip is very complex, they do a lot of behavior modeling. Are you guys familiar with the behavior modeling? But by the way, before I go, I'm assuming everybody has an engineering background here, right? So you guys are familiar, even if I go at the transistor level and talk about gates and all that, I don't have to describe that. Okay, okay. And yeah, looking at the audience online. So, and so like the behavior modeling comes before you start the logic implementation, because you, and even if you have very well written behavior models, you can do end-to-end simulation, except it's not actual circuit. It's what the engineers have written that model, that how that piece of circuit should behave. Okay. So this covers the first three stages. Once we are satisfied with the behavior models, then you would go into the logic implementation. And again, you see the Pakistani flag on there because logic implementation, synthesis, or verification, all can be done here because it's just a matter of having a computer and the right tools, and it can be done in Pakistan too. So usually engineers design the logic of a chip. They don't reinvent the wheel. There are already IP blocks like intellectual properties that you can purchase, and then you can customize your chip by writing more code or more circuitry around it. And chip design these days is done using EDA tools, which is electronic digital automation. That's what it stands for. The industry currently is dominated by three big players: Cadence, Synopsys, and Mentor Graphics. I'm sure people who are in the IC design world have heard about these companies. Having said that, there is a big emphasis also about open source software. So if you're not working on the leading edge, if you're in academia, or if you're working on a non-leading edge technology, open source hardware are getting more and more traction now, like OpenLane and stuff. And people here at UIT have done a whole chip using open source. But I want to point out there are a lot of kinks that have to be worked out. So you hear a lot about it, but if you're doing a design for a customer, you may not be able to do with open source. You will have to rely on the industry tools. If people have a question online, I mean, how would they ask you?
I'll let you know, sir.
Okay.
If they post a question, then
Okay. Okay, so let's talk about logic implementation. So logic implementation in the old days, when I was working on hands-on engineer, I remember the time when we do schematic capture, like one gate at a time, one logic at a time, do the schematic capture, attach it, and make a register, shift register. But about 20, 25 years ago, the hardware design has already gone towards software. You know what I mean? That the hardware description language, most commonly, one of the hardware description languages is used in the industry for digital design is Verilog. Okay, so this is an example of what a Verilog code would look like. People who do actual implementation would have done this. So instead of doing the design via schematic capture tools, now you write it in Verilog. Once you have done your logic implementation of the design, which matches what your architectural blocks look like, what your behavior blocks look like, then you are ready to take that. I mean, right now your design is still in a software, like in the hardware description domain. You have not taken it to the gate level yet. Okay. Should I pause here and see if anybody has any questions? So far? Okay. Excuse me?
Yeah, at this point, if you can comment on the side. So nowadays, HDR is very good, and also it can move.
Yeah.
Yeah. Is there any benefit in doing for developing system diagram instead of the very log? That may help us in synthesis or implementation or something like. Why there is another system diagram?
Well, I think what system Verilog allows, because Verilog otherwise is more specific to block level, but if system level, it will allow you to more interface blocks to blocks. So, I mean, that's what the emphasis is, right? That all your simulations should be done at the system level, right? Is that what your question is? Am I answering your question?
Yeah, actually, and it's a role started.
Yeah,
And the other language was really here.
yeah.
Recently, I've seen a system diagram dialogue. Yes, some different, it's similar to, but in some cases, properties. So I was wondering, who are working right now in dialogue and who are going to start working on it. Should this continue with the dialogue or system dialogue, some kind of a new or better version of dialogue that you should start?
So I should be the first one to admit that I'm not in IC design right now. So I'm not familiar with all this, like the newer tools coming. But if it is just from the name, I think it would give you more advantage to do at the IO level, at the system level, rather than at the block level. So once you are satisfied with your HDL or your Verilog block level implementation, now there are two routes that you can go. Okay. In the old days, you could have gone right to synthesis towards your chip. And by the way, what is synthesis? Synthesis is a process of converting the Verilog to a technology-specific gate level design, because right now it's still in software. So what synthesis will do is take your code and take it to the gate level netlist. And I think everybody understands what a gate is. Gate is usually made of 4 transistors, like the AND gate or the NAND gate. Now, since the chip design process itself is so expensive, costs like billions of dollars to have a mass set and do the fab cycle. So in the industry, there's more and more emphasis to, in parallel, you're doing the synthesis towards the IC, but you're also doing synthesis towards FPGAs, okay? FPGAs, you cannot emulate the whole design end to end, but you could have multiple FPGAs where you download your blocks, and the FPGA, as you all know, stands for field programmable gate array. So you can program those gates to implement the circuit that you have. And once you have those FPGAs, then you can go to the lab and do an emulation. I don't call it simulation, because simulation is something that you do on the computer, but emulation, then you have more and more confidence that the design that you have implemented behaves the same way. Because if you have to make a phone call on a modem, so you can synthesize your design to an FPGA, bring it to the lab where you have all the equipment, and on a lab environment, you can technically make a phone call on an FPGA design. Then you have a lot more confidence that your actual design, when you synthesize it to an IC, it would behave accordingly. Are there any questions so far? So I didn't talk about analog circuits right now. All my conversation will be more about digital design, but you could have analog or the mixed signal design. And the mixed signal design You can do it by schematic capture and then simulate it using SPICE. But if you have to do like the mix signal simulation, what I saw in the industry that I was working as an engineer, obviously things would have changed now, that you would write a behavior model for your analog block and attach it with the rest of your Verilog blocks. And then you still would be able to do digital simulation. But the catch here is if you make a mistake in modeling your analog block, your circuit would come out with a functional error. Somebody who's working right now on the tools might be able to comment. I know that there are mixed signals simulator when you don't have to rely on the modeling as much. Okay, so far the design is still at the gate level, and assuming that we are happy with the results from the FPGA validation, we are happy with the synthesis we have done. And by the way, when you synthesize at the gate level, you get a gate level netlist, you rerun all your simulation that you had done for the Verilog netlist. Now you rerun it again at the gate level netlist. But once you're satisfied, then you go to place and route. Now the best way to explain place and route, if you look at the printed circuit board, you see how all the components are laid out. Now you're going towards the physical design of what you still had at the gate level. And let me give you the example. So this is an example of like a layout. And this placing and routing of the gates is done by automatic tools like APAR, automatic place and route. It takes your gate level netlist and starts laying it out in a physical domain. Here is this gate, which is essentially made of transistors, and it starts laying it out. And these wires that you see are like the better connects that go between your circuit blocks. Now you have a lot of control as a physical designer. You have a lot of control that you can tell the tool what your final layout should look like. Where do you want your RAMs? Where do you want microcontroller? Where do you want this block? You can manually go and play with it, or you can use the tools. People who work on the physical design are really like artists. If you look at it, this looks like a piece of art, you know. And I've seen people in the dark room for hours just playing with the layout until they are very happy. You know, obviously there are a lot of other constraints too, that you don't want to play one very noisy block with a less noisy block. You want to have insulations in there. And the tools usually warn you, but intuitively, people who have been doing the physical design, they have a very good understanding of what to put where. Now, once the layout of the chip is complete, there are some post-layout verification steps. One important step is called LVS check. Sorry, should I just stay here?
No, you can move around.
Okay.
No,
Okay. So,
well managed.
okay. LVS step is layout versus schematics. So you had the digital schematic, or you had the schematic level of the gate, how each of the gates are connected. But then when you went into layout, you want to make sure that every node in that schematic has a presence or has a matching node on the layout, because tools can make an error. So you do a check that every node on the layout has a matching node on schematics. So that test or that check is called LVS. Another check that is very important is called the DRC, design rule check, because the foundry where your chip is going to go for manufacturing and which node, they have very specific rules of what should be the gate length and the spacing between the interconnects and the spacing towards the edge of the periphery of the die. So they send you a check deck. So you run your whole layout through the design rule checks. Okay. Now, all the simulation that you have done prior at the Verilog level netlist and at the gate level netlist, you're going to rerun the simulation because now you would have exact parasitics, like each node has the capacitive loading and the resistive loading. The tools extract that load, you attach it back and rerun your simulations to make sure that your signal doesn't go through degradation because of the load. There are now electromagnetic interferences because the chip is running at such high speed and such small geometries. Okay, so those all have to be taken into effect. So once you're also completed your post layout verification, at this point, your chip is pretty much ready for fabrication. Okay, your chip is ready for, there are different words used, fabrication, manufacturing. I want to point out that so far our chip is still in the software domain. Like even this layout that you saw is still on your computer. Like nothing is made physically. Now in the old days, all this data used to be put on a big magnetic tapes. I'm talking about 1970s and 80s. And then that tape had to be shipped to the foundry, wherever the foundry is. So that's where the term comes out of tape out. Okay. When you send the data to the foundry for manufacturing of your chip, the term tape out comes, and that's usually a time for a big celebration because a big milestone has been achieved. Every company I worked, as soon as the design starts, they start working out what would the tape out party look like, because engineers are quite tired by that time and they deserve a celebration and a little break. So far, the design is pretty much in your computers. Once all checks are run, you are now ready to go towards manufacturing. Okay. Are there any questions so far? Okay. So you notice towards the manufacturing of these stages of mass making, wafer fabrication, and wafer probe, the Pakistani flag is not here right now, because these are very expensive industry. To set up a IC fab cost anywhere from $10 billion to $20 billion. Okay, so it's very expensive. And let me fast forward to this slide, the fab issues. Chips are becoming so dense, like trillions of transistors on a single chip. Back in 2001, there were 17 companies worldwide who were making advanced chip. Today, at the 3 nanometer node, even Intel has dropped out, and now you see there are only 2 big players left, Samsung and TSMC. Okay, so on and off, I saw a press release by a Pakistani minister saying that we should go into IC manufacturing. I think his minister's name was Fawad Chaudhry. And I said, no, I think you're in the wrong track, because these are so expensive propositions that most developed nations have got out of it. Now they are going back into it. So Pakistan can right now not afford to go into the mask making or the wafer fab. Now, let's talk about what is mask making step. Your data of your chip has gone to TSMC or Global Foundries or UMC or SMIC. what are they going to do with the data? They have to convert that pattern that you send, the data that you send, and they basically have to fabricate your gates or your transistors on a silicon wafer. And the way they would do that is that they first make these big masks, okay? And that mask helps them create the patterns of an NPN or a PNP CMOS transistor on silicon wafer. Let's go into a little bit more detail of what is an NPN or a PNP. Everybody here, I think, knows what an NPN or a PNP transistor is. You see, this is a P-type substrate, and in there you will need these little tubs of N-type windows. The reason I'm showing you is that I'm going to show you how that process is implemented in the wafer fab. So first, what they do is take your simple silicon wafer, and then you grow oxide layer on it. And yellow layer photoresistant, but like the photo. Now you see this little opening here? This opening is basically to create this N-type or P-type tub here. Okay. Now, once that opening is, you're going to expose the whole wafer along with the mask to ultraviolet rays. And wherever there is this opening, ultraviolet rays is going to go and react with the photoresist, and the photoresist could be etched away in the next step, chemical. Now you see now there's a nice window here, open. So the red portion is the oxide window. Now, what is this window? This window is open for you to implant your P-type material or N-type material. P-type material is an element like boron, or N-type material is an element like phosphorus. Phosphorus, going back to my high school chemistry, I think phosphorus is an N-type material, so it has an excess electron in the valence bond, and boron has a deficient of electron. So basically, once you keep on repeating these patterns, you keep on putting this mask over and over till you make these stubs, N-type and P-type. And this is how the transistor will start operating. And this is your gate right here. This is, I've got another diagram. This quickly shows you the flow. You have a wafer, you're going to polish it, you're going to deposit your silicon dioxide, expose it with the ultraviolet rays. Once you have the wafer on, the print is developed. You do the ion implantation for your N-type or your P-type, and the resistance removed, and this whole cycle is repeated over and over. To do our existing silicon design, you could have as many as 20 to 50 masks to complete the whole design. Okay, because once your implantation is done, then you have to go and do the deposition of the metals. Think about when you're having a printed circuit board, you put your chips and you put your resistor and diode. In the end, you have to connect them with a wire. If you have a breadboard, you're just connected. So the same thing happens during this silicon manufacturing. Once your transistors are made, then the last few steps is called the metallization, because you're doing the connection of all the gates. The very last step is the passivation layer. So they are not contaminated anymore. One thing I wanted to point out, right here, is all of this has a passivation layer except your pads. Pads don't have the passivation because that's where you're going to come and make the contact to the outside package. So once you're done with all the steps, here is what a finished wafer looks like. Finished silicon. See, when we started out, the wafer size was smaller, 4-inch, now we're up to 12-inch wafer. So depending on the size of your circuit or your dice, you can have hundreds or thousands of circuit or die. Each circuit is also referred to as a die. So you can have that many dies repeated over and over. So your wafer is fabbed, as we say, or fabricated, but it's still not tested. Okay, because you can, silicon by itself can have defects, and one of your circuits could be prone to a defect. So every die in here has to be tested. So that's what this stage is called, the wafer probe test. You would take your die, and this is an example of what a wafer probe card looks like. And you see in here, these little probes, they would go and make contacts to the pads that I've shown you earlier. So you will be able to send the signals, inputs, and measure the outputs to make sure that your die or your circuit behaves the way you have designed it. One thing I want to share, the testing that you do on the circuit is actually your same simulation code that you have for the necklace. You now convert it and bring it onto your IC tester, and you're now exposing your actual silicon. You're replacing the silicon die with the necklace that you had before. I've given an example of what a probe tester looks like. This people who have worked in the lab. On the left-hand side is what an engineer would work in the lab to, if there is a bug or a problem. And even now, it's becoming very difficult for engineers to work on probe stations because the geometries of the technologies are so small that you handshake a lot more to go down and make a contact for silicon, which is 7 nanoseconds or 5 nanoseconds. So a lot of it is automated, but in production, this is what a wafer production looks like. You see this tester that has your probe card, which is inverted, and down below is the wafer. So the probe card comes and makes the contact with each die, and then once the die is tested, then it moves to the next and next. So then you end up probing your whole circuit, and once you're done with it, this is the tested wafer looks like. We call it like the wafer map, and this is the pinning. So you see the green dots, that means it's good, and yellow and red usually means bad, and yellow and different shades that you can give depends on the grading. Your circuit may not perform up to speed or on temperature. You can still use it for some other application. You don't want to waste it, so we call it pinning. Some premium customers, they want the chip to be operating at minus 40 to 85 degrees, but then one chip will only work at 70 degrees plus to 0 degree. If you don't want to waste it, you can sell that chip at a lower cost, at a lower price, sorry. I think we already talked about fab issues. So you're done with your wafer testing and you have each die, whether it's good or bad. Now, what do you do with it? What you do is go back and use like a diamond saw to cut this, or saw these out, and you have individually die. Now, you cannot work with an individual die. It still needs to be packaged. So packaging is now becoming a very sophisticated industry. There's so much technology now in packaging. Now, again, you notice I don't have a Pakistani flag on packaging because packaging, again, is quite complex industry. You need clean rooms for that. So initially, we can leave it for offshoring. Packages have evolved from very simple dip packages to wafer scale package, like very tiny. The tinier the better, the less plastic and less periphery around it. This is what a ball grid array looks like of a flip chip packet. And what I want to point out that you see these little bumps here. This is your die. And in the old circuitry I showed you pads at the periphery. Now you can actually have bumps, and then you put the ball on the bumps and you flip your die, and it interfaces with the package. And these are the balls outside of the package that's going to go interface on your printed circuit board. This is an example of the wafer scale package. The package is almost the same size as the die. I had another example of a chiplet. It did not make it to my slides. So there is another technology now, because like the bigger your silicon die is, the chances of having a defect is higher. So now since we want to really cram a lot more circuitry, there is push towards having quite a few smaller chips on a substrate. We used to call it MCM, like the multi-chip module. Now we are calling it chiplets. Okay, so that technology is also coming along. So we are done with the packaging. We got the package done of our die back at a packaging house in Korea or Philippines. They're everywhere. Malaysia, Singapore. Oh, I can start now. No. Oh, okay. Okay, so now we still need to final test, because you could have introduced a problem during packaging of the part or packaging of the die. So you still need to final test it. And this is what a final test setup would look like. This is like an IC tester, Teradyne, LTX. This is the test set. When you are at the engineering level, you would take one part, put it on the test bed and test it. And once you're happy that your chip is the way you had designed, because most of the time engineers find it difficult to work at the wafer probe level. So you will probe it, get it packaged, and bring in-house to whichever company or industry you're working in, and then you test it. Once you're satisfied with the test, this is what an automatic handler looks like. What is a handler? Handler is where you can feed tubes and tubes of these package parts. It will come and dock with your tester. Okay. And once one part is tested, it gives you a single grain, and you suck in more parts. So the throughput is very fast. If your test time is 3 seconds or 10 seconds, just all day long, 24/7, it's going to be testing your parts. And now you have a final tested part that is ready to be shipped to the customer. But before it gets shipped, we usually bring it back and do more system level validation or verification. Basically, now is the time, if you remember me talking about FPGA in your lab, you can remove that whole FPGA circuit and replace it with your final chip and rerun your test suites, because that's where your customer is going to be working. If you're working on a cell phone device, you put it on your cell phone and drive around the crowded streets of New York to make sure it works as the chip was designed. But there's 3 to 6 months worth of silicon verification that's done before you say, okay, now the chip is really ready to be shipped to the customer. So I think that I walked you through all the phases from chip customer specification to design, mass making, probe test, packaging, final test, and system validation. Are there any questions, or have I gone too fast, too slow? So why semiconductor industry for Pakistan? I think I talked about this earlier, that chips are now powering everything from in our lives these days, from your kitchen toaster to phones to equipment in the defense industry. I mean, you just see what is happening in the world and geopolitical tensions. If our defense equipment cannot have the chips, I mean, our equipment is struggling. So I've done some research and found out that each country has realized the importance of the semiconductor industry, and they're investing billions of dollars. And this is just happening in the last couple of years. US came up with the CHIP Act, $52 billion. EU's CHIP Act is 49. China, I cannot come up with numbers because they don't publicly share. India is committed to 10 billion. So Pakistan has come up with its own national semiconductor plan, and the plan is to go into the low-hanging fruits, okay, of IC design. We train our students here. There's Advanced Technology Institute that Dr. David Shirvani's plan talks about, that we bring our engineering graduates who choose or who get selected to be in those ATIs. They go through an 8 to 10 months of training in IC design, verification, and then we absorb them either by opening up the design centers or invite foreign companies to come. We have these trained people who can go into the IC design cycle. And it's equipment-wise, money-wise, it's not that expensive. And other thing we can do is also to go into like the final test, because IC testers are expensive, but they are still in millions, not in billions. Couple of $1 million, you can have few IC testers, and when the chips are done, we can test them in Pakistan and ship them to the customer, the final customer of our customer. So like a company at Intel or Qualcomm, once their parts tested, they don't have the capacity, they can be sent here. And to set up few IC testers is not that complicated. So I know that the Pakistan Semiconductor Plan also talks about light manufacturing in Pakistan, and that's what they are that's what they mean. And one other good thing, if we have IC testers in Pakistan, it would also help, even if they are in Islamabad or Lahore or Karachi, wherever, these testers you can remotely log in. So if we have done the designs here, it gives our engineers an ability to test their silicon or their package device on to an actual tester, which is a big challenge because you can do academically or even for an industry of design, but you still need to test the real silicon. So even if those testers are used for production purpose, few hours a day, they can be dedicated for engineering work. And engineers could be sitting anywhere in Pakistan, remotely log on to the tester, have an operator there who puts the device in for you, and you test it. So that completes this aspect. I had another presentation too, which talked about my own journey from IC design. I'm not sure if you guys are interested to hear about that, or do you have more questions about the IC design or the challenges? Are there any questions of people on Zoom?
No, nothing. There's an announcement I would like to add, as you mentioned that UIT students have submitted design in open shutter activity.
Yes.
Right, so under the banner of the MERL,
Yeah.
Also, DS is a part of that. We have also submitted two designs from DSA Super University, one in MPW and one in MPW4, which we will carry in papers of that. And we are also planning to submit a design in MPW6, which will going to be announced in a month's time.
So the MPW2 and 4, you guys have been already approved?
Yes, we are actually, we are under the banner of world, we have submitted our designs there. So we have gone through all the process we have mentioned here, like APR process, pre-verification, post-verification, RTL designing and all of that stuff. So I just want to add that this is
Good.
part from the DHU Super Institute and also that we will be receiving those shit here in DHU in a few months. inshallah.
Right. So is that the same circuit that you were talking, Dr. Sabir, when I was here two weeks ago? That I think the sixth one is still in works, right?
Yes.
But two and four. So is it 2 and 4? The circuit, could you describe what that circuit does?
So for the second schedule, we have submitted our design of a bulk SOC. It is a simple four-stage pipeline code which have a simple UI programmer around it, which controls the normal execution is RB to IMC code. And for the MPW4, we have submitted our design which contains two type of memories. This was a test of our product which we have developed under model is of a RAM generator, which we use to generate multi-level of memory. Like if you have a base memory of 1 kilobyte, for example, so you can use that generator to generate more memories of 2 kilobyte or 4 kilobyte or with multiple cores. So for that testing purpose, we have also included that RAM generator generated memories into that MPW4 setup. So one is a code and second one is a memory.
So the Shabbir 2 and 4, have you seen the package parts back?
No, it is in the process under the fabrication from under the Google.
Yeah, Google.
So they will be started receiving as we have recently received the first shuttle in UIT. So we
So that's at Skywalker, right?
yeah,
And 130 nanometer
130
process. So what kind of competition did you face when you submitted? Because that's open worldwide, right? So
it was actually there was not competition because the designs were on 40 they accepted and we were actually submitted design into one. So we have a good image of ourselves from the world.
I
So
see.
that's why we have again submitted 4 design actually from the world, 2 from DSO and 2 from UIT in MPW2. And in MPW4 we again submitted 2 to 3 designs, 2 from UIT and 1 from DSO.
Mhm.
And inshallah we are also planning to submit design in MPW5 also from the UIT. The team is working and inshallah MPW6 we are also planning to submit. So,
So-
like a team effect effort we have.
So if I'm, correct me if I'm wrong, from 2, so 1, 2, 4, and 6, Pakistan has a seat on that shuttle, 5. So the only one we missed,
One has moved this of
3. Wow, that's, and how many seats are there on the shuttle?
mostly there are 40.
40 seats. And how big is a seat in terms of the die size?
It's actually 10 mm as well.
So whatever you can put in 10
We
minutes.
can put, actually we have put in like SOCs like Azadi, Ibtida Azadi, they have also mentioned from the UIT side. And we have also implemented the bulk SOC from
So did you guys have any extra space lying around which you did not use, or did you end up using all of that space that was available?
actually that will be a little bit difficult for me to answer because that part was handled by our APR team, our leads were working on the APR side.
No, but when you look at the layout, can you tell me? Oh, look
Actually,
at-
which is not mostly covered, that was
Yeah.
some spaces like because of the memory, we have to keep some spaces between so that area should be that.
Now with your multiplex IOs, you can have like different circuitries within Pakistan. Somebody else can share the seat with you if you have
It's
Yeah.
another plan, we are also working on the share.
share seat. No, I love this concept. It maps very well with a plane seat or a rocket seat. You have so many seats in the rocket. Rocket is gonna take off, you be on time, and you behave accordingly. You know, you run all the tests, all the checks, and then it's totally free, right? I mean, yeah. So, if you are you interested in some of my own experiences in IC design? Do we have time? Can we go there or okay?
There's a question from Ms. Tessin. Sorry, Sir
Yes.
Tessin, Dr. Tessin.
Okay.
Assalamu alaikum, sir. Dr. Tessin is here from JS. Can you hear me?
Yes, I can hear you.
Oh, thank you. Good. First of all, congratulations to you. You presented very well. It was a very nice and informative talk.
Was it
My
too fast?
Thank you. My question is that, okay, once we have fabricated our IC, our customized IC, and if we want to, let's suppose, increase its frequency response or its time response, so how we can we make some changes, or what should I need to do? Do I need to give some specification related to the diode level or transistor level, that what should be the doping or what should be the gate length? Do I need to provide those information along with the IC design, or it is just we are dependent of the manufacturer, that what kind of process they are using?
So that's a good question. If you want to do any,
Sir, can you please repeat the question so that the audience can also?
okay. So the question is, and Dr. Tassim, please correct me if I didn't get your question correct. So the question is that if he wants to make any modification to the frequency response or any other parameter, does he have to work with the design team, or does he have to work with the foundry team who's gonna do, right?
Or
Yeah.
right, sir. Right, sir. Right.
So my question is twofold, depending what kind of relationship you have with the foundry, if they can tweak the process for you. Because if you are a big guy, they will accommodate. Otherwise, I'm speaking from my experience, if otherwise you would have to modify your design to meet their PDK deck or whatever they can deliver, whether it's spice response or it's the digital response. And I've had personal experience working for a smaller company and dealing with TSMC, and working with Qualcomm and dealing with TSMC. The response of the foundry was very different, because when I would go to Taiwan, working for a small company, they won't even send somebody at the airport to pick me up. But when I was working for Qualcomm and I would land in Taipei, there would be like a Mercedes standing for me to pick me up. So foundries behave differently with the different customers, depending on your cloud. Did I
Okay, sir.
answer?
Yes,
Yeah,
sir.
sorry.
Thank you. Thank you.
Yeah.
Thank you for your answer. But now I have a second question. If please, if you allow me to ask.
Yeah, sure.
Okay, thank you. Yes, with this, we can conclude that okay, we are learning, we are focusing on this IC design part, but we should also try to get the fabrication facilities also. We should also focus on that because I'm a my research area is semiconductor, and my focus area is fabrication part. So with this, because just now we all know that recent is Ukraine and Russia conflict, and I have gone through an article in which there is written that nowadays country's sovereignty is related with the independence in semiconductor industry. So
Yes.
and recently in US Senate has passed a bill, and in which now they are planning to invest 300 to 400 billion dollar in semiconductor industry up till 2030. So now they are
Mhm.
realizing that China is dominating and they are lagging behind. So that is why now they are planning to invest in semiconductor. So we must look
So let me,
into.
okay, so let me repeat your comment. What Dr. Tassin is saying that I talked about IC design and said IC design. He's advocating that we should go into wafer fabrication too in the manufacturing and quoting examples of US. I know that US is going and setting up a fab in Arizona. They're setting up, when I say US, I mean Intel is setting up a fab in Arizona. TSMC is doing, Intel is setting up another fab. But Dr. Tessie, those are the still very expensive propositions. If Pakistan has to go, I would say we should try to go for the older geometries, which the developed nations wants to get rid of. And they still have a lot of legacy devices. There are still a lot of devices which don't need the 5 nanometer and 3 nanometer devices, even 135 or 65 nanometer, we can set up a foundry there, but that's still at the national level. So I agree with you, but I think we should start from the design cycle first. Okay? I didn't hear yours. Okay, so
Okay, sir. Okay, thank you.
yeah, okay,
If you allow me, may I ask one more question?
sure. No one
Yes,
else is asking, so
thank you. With this, the comments which you have made, this also leads us towards another conclusion that, okay, TSMC is having a technology up to 7 nanometer. Samsung is up to 5
I
nanometer.
don't think.
So we can start with the 20 micrometer, which is currently available only for the $10,000 rupees. So we can
Yes,
start with bigger technology, which is very common, and we can acquire that technology rather than
no,
going
I
up to
totally
the
agree.
extreme point. If we are developing our ICs for our kitchen or for our vehicles,
Sure.
there.
And this
Uh,
is, yeah, I totally agree. We can start there because this is how Israel and India, because working for American companies, I have seen them come and take this technology from us. And they've usually taken the non-leading edge technologies first and got themselves better at that. And then they like moved up. Like if Israel today has an Intel foundry, it was not always there. I think India does not have any foundry. They did try to go into it, but they had to drop out. So no, I totally agree that we can go with, say, 130 nanometer.
yes, absolutely. Thank you, sir. Thank you. Thanks for.
Yeah, no, totally. So how are we doing time-wise? Do you want to go through my other presentation briefly?
Yes.
Okay, किस तरह का वो जो flash drive पे है ना? So the second part of the talk maybe to help you that I walk you through my journey of how I went from Pakistan to Austin, Texas, then Ottawa, and then back to San Diego. And now I'm trying to spend a lot of time in Pakistan because it's really satisfying. I can do so much work in the US or Canada, but I hate to say that, but those are still my adopted country. This is my native country I was born in. So whatever I can do to promote and bring the semiconductor industry back here would be very, very satisfying. So I'm going to full circle the PowerPoint. Is this a PowerPoint? Yeah, is this a PowerPoint? Indeed. Okay. And this should not take more than 20 minutes and I'll open it. So I started off obviously in Pakistan. Full circle. Cross. Presentation mode. Okay. So I started out in Pakistan and I went to engineering university Lahore. But in those days, the universities, the schools were closing all the time, strikes, and I got tired of it, so I transferred to UT Austin. Okay, so not UT, sorry, UT Austin, University of Texas at Austin. There I focused our program in UT Austin. Screen sharing. Screen sharing.
Take a minute. Okay, that is. सही आगे
Okay.
अभी सब आगे
Yeah, the reason I named this presentation full circle, that I've come back to Pakistan full circle. We started out from here, studied and worked in a lot of different, I mean, not a lot of, mostly US and Canada. But, okay. So I'm going to focus on the first part. Screen share holding. Okay. I won't even attempt to do this. Dr. Sabir, that's okay to understand? Okay.
Yes, sir.
Okay. So, and University of Texas has a very good program. I'll forward you on. Thank you. So I think like one of the things I want to share with the young people that even at University of Texas, I had a very good position as a research assistant, which was paying me well, and I had got in-state tuition. In-state tuition is like if you're paying $4,000, in-state tuition is only $400. But towards the end, I said, this is not where I want to go. I want to go to a chip company and work. So I left that position at the university and started out as an intern at the first semiconductor startup in Austin. So sometimes you have to lose something to gain something. And I think that was one of the best decisions that got me on foot in the semiconductor business even before I had graduated. Because research assistantship at the university was in physics. That's not where I wanted to go. I wanted to go into the chip design, testing, and simulation. So my first job was at Crystal Semiconductor, which was later acquired by Service Logic. And that's something happens a lot in the US. You start out a company, if the product or the service is good, either you go public or you get acquired. So in that case, we got acquired. But one of the things I learned in the startup, which I wanted to share with you guys, is that I had to wear a lot of different hats. You could not just say, I'm a product engineer, I'm just going to do the characterization of the device. You had to do some design, you had to do some tests, you even had to talk to the customers because you were like 10, 15 people. So if somebody were to ask me, I learned 3 times as much in a startup than in a bigger company. So what I learned in a startup within 1 year, in a bigger company, it would have taken you 3 years because your roles are more defined. But having said that, I think you need both, especially in a business like semiconductor, because the chips are so complex that when you work in a big company, it's very process driven. So, and like the chip that Intel or Qualcomm does, there are hundreds and thousands of engineers working across the globe. Somebody working on one block, somebody working on one block. So they have to be very process driven. So when you work at a bigger company, you don't learn like for Pakistani language, it's really value there, right? But then there is somewhere to be very process driven. So even when we have APIs and when there are companies that are going to come to Pakistan, our engineers are going to learn a lot when they work with big American companies or Chinese companies because they will be process driven. That will prepare you then to go start your own company in the chip business because the barrier to entry is so high. If you are specialized in chip design, the rate of success is fairly high than if you go in a startup in e-commerce or something like that. So at Crystal, I wore a lot of different hats. And then my next assignment was at Metallization Semiconductor in Ottawa, Canada. That's how I moved there. And one thing I learned, Mitel being a big company, very process driven. That each stage, we had a validation phase and a planning phase, and you couldn't go to the design phase till your planning phase was complete, all things were checked off. So that's something that has stayed with me, what I learned in a big company, very process driven. So at the startup, yes, you had the benefit of learning a lot of different things and very flexible, but a big company. So I ended up working at Mitel for 10 years, but it was in Ottawa, Canada, and Canada is very cold, as you would know. And one day there was a turning point in my life that I shared. I woke up in a cold morning in January, and I saw my car right there buried in snow. And I said, no, I need to get out of here. This is too cold. I'm from Pakistan. And so that's when I actively started looking for opportunities down south. And I had quite a few opportunities, and I got a job at Connection System Rockwell, which was later spun off. So I moved to sunny San Diego. One interesting thing in the life of the mergers and acquisition, I started working at Rockwell. One of our network access division was spun off as Connection, which one part of Connection was further spun off as Mindspeed. So you see, you could be working at one company and there's always this change, turmoil, either you're acquired, you're spun off. So I started from Rockwell, but then I left Mindspeed. And the reason I left Mindspeed was because I was living in San Diego, and San Diego is wireless valley. All these products were more like wired, 56K modem, T1E1 line. I wanted to go into the wireless business because that's where the action was. So I didn't go out to Connection. I got some management degrees. I went to join a couple of startups, which was working in those days in Bluetooth and wireless LAN. One startup, we did very well. We got acquired by Microtune. We made some good money. The next startup, one of the experience again at the startup was that even though I had like the design and test background, I was sent overseas to Malaysia and Singapore because one of the chip were having a lot of production issues. And this startup had made a commitment to the Wall Street that this quarter we are going to make this much revenue. You couldn't make the revenue if you could test the parts. So that's again going to a startup. I would have never envisioned that I would have to live for months in Malaysia and Singapore. So that gave me exposure. This startup, Jala, was one of the Indian guy, and you know what the word Jala means, network. So he came up with the name, but that was after 9/11, and we never got the funding. I worked here for a long time as one of the founders. We didn't get the funding. I said, Shabbir, time to make some money. So I went and joined Qualcomm. One of the things I wanted to share with Qualcomm is that even though it's an established company, but the reason it's so successful is that the really mindset of a startup. The way to describe Qualcomm is a startup with a positive cash flow. In a startup, you always have to worry about money, funding line, funding Khatamori, Series A, Series B. Qualcomm, we didn't have to worry about money, but the work environment was very much a crazy startup. And one of my assignments there was to bring about a CDMA chip, very cheap, such that it goes into $20 headset. And this was in year 2005-06, because they wanted to bring CDMA technology to develop it for India and China. So my assignment was not high tech, my assignment was more of a business. How do you remove this extra circuitry from Qualcomm's very high-end chip and make it a very small chip that can go into a handset and then they can go sell that handset and even in China for $20. So that was got a lot of recognition and awards, shipped a lot of devices. And after Qualcomm, I had an itch to do something bigger. I think I realized as you go into executive management, your job becomes more like a therapist job, you know. So, and I was doing a lot of counseling, like people would come to my office and say, "Sir, why am I not getting promoted? Or why am I not sent off this training?" So it would be very good to go back to school. And that's when I took a sabbatical and got a master's in psychology and counseling. I mean, full circle. Basically, now my role is how do I promote semiconductor ecosystem in Pakistan? You know, I have a lot of connections in the US, worked in that industry, and now I'm going around. I've gone to PFKEET, I've gone to NED, I've gone to UIT. Today I'm here at DHA, and basically find out what are the gaps between where academia is today, where the industry is, and how can we quickly train our youth to go and contribute towards this new awareness worldwide about the chip business. That's all. So that was my summary of from Pakistan, US, Canada, US, and yeah, in Pakistan. Are there any questions in that part?
Ask the questions and please move to
Dr. Billy?
Over deep.
I think.
Career of that maybe for me of what do you recommend to this student? Should they go for masters first or who directly, because they're just running their FIP platform.
Yeah, you're final year program.
They'll be going for master or eventually in Pakistan, the parents sees the schools must earn after
Yeah.
completing their graduation. That's the main mindset. So what sort of advice that will be giving to these students who want a career path or career change?
So for that, I'm gonna wear my psychology hat, okay?
Yes, sir.
And I'm gonna say, आप अपने आप से पहले पूछें, what is it that you really want? Because that's where the success really comes from. I mean, your parents can say one thing, your advisor can say one thing, but if you want, I want to go in the IC business, in the chip business, and I can work for a company for a couple of years, that's fine. If you say, no, I really want to specialize more and do my master's, I can't comment on the financial aspect because I have to take over, but then I've seen people go work for a couple of years and then go back and do their master's. And from what I understand, Pakistan, but the academics are not as expensive to do their master's, right? I mean, tuition fee and all is not as expensive in the US. So,
So basically my question was कि एक confusion है मास्टर और इसी हवाले से सवाल
जी।
कि confusion ये कि ऐसा लगता है मुझे अपने छोटे से experience से कि if you are engaged with a project or in a project तो project based learning होती है it's more efficient or it's more beneficial than the academic learning that we do in classes. So this is way of learning है. तो इस सेमिनार को ये सोचते हुए कि हवाले से हम प्रोजेक्ट से करें तो would you recommend लर्निंग के एतबार से कि हम मास्टर के एकेडमिक्स की तरफ से प्रोजेक्ट्स में स्पेशलाइजेशन के लिए या नहीं you would say कि stick to the project based learning or do projects and stick to a company or किसी laboratory के जो एक project करती हो or learn from there. What is your recommendation?
my personal experience was project based because you have seen I've continuously gone back to school and done, but that's when my inner voice says, okay, enough project based down, you go back to school and get another qualification. So that's one approach. Other approach is to go all the way to academics and then go. But sometimes when you're all the way in academics, you don't really know what you want. And then you get all the degrees and then you find out, oh, that's not really what I want. Because you have an opportunity to do project-based work and make some money, get some experience. I would go that route. I don't know about the professors and so on. What do they have? So, because I think undergraduate degree, since I'm talking from the IC domain world, and that's one of the questions I had for the professor when you asked. Okay, and that's Dr. Sabi, I think we were supposed to get together your curriculum. How does it prepare right now the students to do like parallel coding, net listing, verification? I would say all the way to GDS2, tape out. What are the gaps? Because if the students are prepared on that, I mean, they can go to the industry once they graduate. But if there are gaps, then it means it will be hard for them to do project-based work. Mhm.
Even within that, work on but then after that, the we are actually working in Paris. We are trying to keep up with the time. All the mistakes that we talk to. Once we are done at 9, we the maximum thing that we can do is
Till FPGA. Okay.
Started there are three was from the very basic design. One is
So in the VLSI design course, can your students do the role of coding and synthesis? Okay, you have synthesis towards FPGA, not IC, because IC you guys have never done any fab. At least that's good. No, because still FPGA is very good, because in the industry also there's a big emphasis now towards FPGA. Some designs are done only on FPGA, you know. So that all the more and more companies want FPGA engineers to help them do the validation. So I'm thinking in terms of the job opportunities. Okay. Mhm.
We are also looking for the FPGAs which are like mountable on the design, so we can take them out and put in other PCBs. By that, I think we will be able to produce some of the parts to the
Actual circuit bun जाएगा. Okay, that's one. So, you know, I had asked Dr. David Sharwani to share with me more details, and he said he will publish. So people like you who are in the IC design, cycle would be a big asset, because वो काम आ रहा है advanced technology institutes where like any gaps जो आपकी knowledge में है, you can go learn there, and you finish from that training in 8 to 9 months, and you're an IC designer, and the world is open. I'm not suggesting you leave Pakistan, but now the jobs are coming to Pakistan. You can work for a company who's doing IC design in China or Europe or US, and do it as long as you have internet access and they give you access to the tools. So that opportunity is there for you to do the project-based work. So आप समझ रहे हैं ना कि वो opportunities अब आ रही हैं.
If you have mentioned that we work on more than 500 million chips, so what type of chips are they? Processors, microcontrollers, or
Oh,
specific
500 million.
applications?
Yeah, so that was CDMA cellular in a high volume. Volumes have been shipped, and every time your customer comes up in highly dense population countries like India, China, so the volumes really ramp up. So my background has been always like wireline technologies up until I moved to San Diego, and then I switched wireless. So wireless is Bluetooth, 802.11, A, B, N, and then GSM modem, CDMA modems, and all the cellular phone chips. Actually, I managed the development of the first Qualcomm chip, which was taken into Apple's iPhone. I was managing that coming into that. So my background towards the later part became more cellular. Are there any other questions? One last thing, if I may, I had one thing in my engineering lessons is the emphasis when you're doing the design, simulate as much as possible. Simulate all corner cases, because जो प्रति आप लोग simulation में पकड़ सकते हैं, इसका cost silicon or FPGA level पे 10 times ज़्यादा, जब तक वो कस्टमर तक जाता है उसका और 10 गुना ज़्यादा हो जाता है. So if one thing I can, or up to simulation is what I mean by FPGA. अगर आपके पास FPGA की facility है और वो कोड आप अपना FPGA पे डाउनलोड कर सकते हैं. So I cannot emphasize enough. दूसरा एक जो लेसन मैंने यहाँ when you're doing the design of a chip, if you can have a focus of the end product, that really helps. Rather than just focusing on the chip पे या अपने block पे. One of the startup I worked with, our CEO was very good. वो हमेशा कहते थे engineers को कि आप weekend पे जाओ, Best Buy वहाँ store है जहाँ सारे ये modems और राउटर्स बिल्कुल. इसलिए वहां जाके देखो आपकी चिप एंड प्रोडक्ट में कैसे लगी है, कैसे दिख रही है, कस्टमर्स को देखो. So that was one of the best advice that it brought you up from the drawing board to the higher level in the customer arena, because it helps you make the decisions in your engineering world if you are customer focused, or at least you have interface. And it was towards the end of towards the last 5-10 years, it has become very common practice in the US that the engineers go and meet the customer face to face. Not all the time, because otherwise they won't have the time to do the design, but during the specification meeting, because otherwise there's an engineer here, you who's doing the design, and there's an engineer there who's going to use your design. You're going through the marketing teams. There's always things getting lost in translation. So if during the specification or the launch of the engineers from both companies meet, they can quickly resolve so many issues about specifications. And so it's maybe when you go work in the industry, don't hesitate to go talk to the customer directly. Engineering capacity. I can keep on going, but I think we should wrap it up unless you have more questions. No? No?
Sorry,
Jay,
can you comment on system on chip?
who is this up? Are you online, right?
No, I
Oh, sorry. Okay, there are service focus on screen. Jay,
system on a chip.
So- it's a constantly flowing game, okay? So we have gone through SIPs, system in a package, then system on chips. Now, as the system on the chips are getting so complex, that now we are going towards, again, chiplets. Let's break the chips down so they're more manageable. And they are, because if the system gets too big in silicon, the chances of your hitting a defect in silicon is much higher, and then you end up wasting the whole chip or whole die. So I've seen now, talking about the Moore's law, right? The Moore's law is almost coming to an end. Moore's law was that every 2 years your number of gates or transistors are going to double. Now with the geometries getting so small and the circuits getting so big, so I think we are again depending case by case basis. Let's break this part of the system, put it in a separate package. Then you know about the PCI interface, right? They're developing a similar interface for IOs on the chip level. Now that standardized IO, you can be like the Lego blocking. You can take a Intel chip and you can take an NVIDIA chiplet and just build it together with it. So I think it's it's drifting away now again from the SOC. Are you involved in any of the SOC or the system on chip design? Okay.
Actually, what I
Yeah, but-
bigger view of the system.
Yeah.
Apart from semiconductors, like I heard that they had all the microelectronic systems that is in the battery. So
Okay, so when you said system on a chip, I thought you meant system on the silicon.
actually, I'm talking about bigger view, which encompasses not just distribution.
So that's where the world is going. System on the silicon has its constraints because to share with you a personal example, like when we were developing the Powercom, I was in charge more on the MCM side, like the multi-chip module. You have the power chip, you have the RF chip, you have the modem, all on substrate और ऊपर से पैकेज डाल दिया तो बाहर से तो आपको एक ही चिप लेवल है but actually it's MCM like the multi-chip module. Here this is what we know, we have to reduce cost and we have to go on system on a chip in some circuitry को एक silicon पे. So we spent like billions of dollars initially to cost कम करने के लिए, but we found out that the manufacturing issues were so much with the analog circuitry and the line drivers that they in the end up, it was a wash. And then we are back again to system in a package. So these acronyms have been going around depending on your requirement. My personal view is system on silicon only makes sense if it's very manageable, similar blocks. If there are too many discrete blocks, then it's very hard to simulate and have a manufacturable device. ये कहाँ से है? It's something I've had from my management days to always guard your time and have some downtime, because in the Silicon Valley and in the startup, we are seeing burnout so bad. You know, so. कोई और सवाल, कोई और question? ठीक है. Thank you very much, sir. Appreciate your time. बहुत बहुत शुक्रिया आपका. And if you need to get hold of me, then find me on LinkedIn.